Hello and welcome back. Today I want to start a new project, something to fight the shutdown blues, and I'm kind of thinking of reviving something old. And where did I put it? Some time ago I was working on and this here. This is supposed to be a galvanometer. It is basically something that works kind of like a speaker, but instead of turning or moving a membrane, it turns an axis. And these things are really complicated. Not complicated to build. You can build one really simple. But it is rather complicated to get them to work correctly. Galvanometers are used where very exact positioning is required, and it's kind of they're used in show lasers. They're used in SLA 3D printing, and basically the way they work is you have, let's use this one for example. You have a electromagnet, basically a voice coil, and then you have a shaft with a mirror at the top, and this shaft has magnets on it. And depending on the way that you turn your magnets, your electromagnets, as you can see, the ferrite magnets, or in this case neodymium magnets, will turn accordingly. And that's the simple part. The complicated part is in figuring out how far you've moved your galvanometer and then stopping in time. Galvanometers that you can buy, and they're not even that expensive, usually have either optical sensors at one end, or they have capacitive sensors. These sensors can be read really quickly, and they're then basically used together with analog amplifiers and comparators that figure out what the difference between your position and the position where you want to be at is. And once they figured it out, they move the axis accordingly. And I actually built some of this analog circuitry. This here is one of the boards that I built back then. And they're really complicated because, they're kind of complicated because they actually do PID. They do a PID algorithm between the input data and your position data to generate the output, all in hardware. And it's really interesting to build this stuff. But in my case, I just couldn't get it to work. And the reason why I couldn't get it to work was basically this. My idea was to build a galvanometer with a hollow shaft. This is a carbon fiber tube. And inside this carbon fiber tube are 4 neodymium magnets that are oriented so north is on the one side and south is on the other side. So it's not like the magnets that you can buy where north is here and south is there. These have it on either sides of the shaft. And manufacturing this was pretty complicated because you actually had to get these all in line, and then I glued them together with super glue, and sometimes it worked out and other times it didn't, and one of them just went flying away. This was one of my first tries where I was trying to just have a shaft and then put some sort of optical or capacitive position probe at the end. But then I thought, well, I could do it simpler or better. So I thought, that's the way it always goes. And my idea was that if I have magnets in here, and if I'm able to turn this electromagnet at the end on and off again, then it would be a lot simpler for me if I had a magnetic position sensor that I could just shove in there, and this position sensor would tell me the orientation of the magnet. And for this purpose, I actually bought some Hall sensors that are non-latching, and they actually give you a very good position indication according to their position in the magnetic field. So if you turn the magnetic field, the output on this Hall sensor will vary, and basically they do output a voltage between 0 and 5 volts, which makes it pretty easy to use on microcontrollers. And that was the first thing that I did after building all this stuff. I got one of these really simple double H bridge boards, and I just hooked up 2 of these galvanometers to the output of that, and I read the input from the Hall sensor and put that into an Arduino. And according to the difference between the position I wanted to have and what I was reading, I was sending short PWM pulses to the magnets, and that in turn would move the mirror. Now, this didn't work out exactly the way I wanted it to work out, and the main reason for that was because the Arduino was way too slow in reading analog input. So I thought, and then I put all of that aside. I did give it another go with the analog circuits, but the analog circuits have one very small drawback. Because the Hall sensor is actually inside the magnetic field of the voice coil, it is also measuring the signals that it's getting from them. And that has one big disadvantage, being that the PID circuitry in here gets really confused. I was able to have simple positions, I don't know, maybe like with 20 to 25 hertz, and it would get to them. But if I had just very small position changes, the whole circuit would just go mad, and I couldn't get it figured out. And in the end, when I did, I realized that it was all my fault, because the position sensor was basically just getting input from the voice coil, and the voice coil was then telling it to go in the wrong direction, and instead of writing it, it wronged it, and it got successively worse. So I went back and I thought, well, let's not do it, because you can actually buy galvanometers, and they're not even that expensive. You can get a complete set which is rated for, I don't know, 20 kilo positions for like $70 or so. So I kind of cheaped out on that one, and I gave up on it. But since I don't have anything better to do, I thought, let's give it another shot. Let's try to revive the hardware that I still have, which is one of these here. I'm not going to use that one. And I've got a second one of those. That one doesn't have a mirror yet, but I think I can manufacture another one. The mirrors on here are actually they're hard drive platter. A hard drive platter is very shiny, very reflective, and it is absolutely 100% flat, and it's this surface that reflects. There's no glass in front of that, so they make for very, very good mirrors. You just have to break a hard drive and then smash the disk and look for some square shards of that. It's a really simple way to get to some really good quality mirrors. So I've got two of these. They're built very simple. They just have two carbon fiber tubes. They have two bearings in there, and the inner carbon fiber tube has 4 neodymium magnets that are aligned, so the magnetic field is north or south at the right and left side of it, and not at the end. My prototypes, which had much larger bearings, they're actually skateboard bearings, and the voice coil in the middle here with the PCB board, these actually worked slightly better than these do because the air gap between the magnet and the coil is greater on these. But and these do tend to get problems with overheating. But I just want to get it to work. I don't want to make it perfect. And then maybe I can go back and make some more of these. And what I didn't realize, I wouldn't have thought so, the magnets seem to do something really odd with the bearings. The bearings, although they're really, really expensive needle bearings, and they were moving absolutely perfectly when I got them, the magnets seem to do something odd to them. I don't know, maybe the needles are sticking together, maybe something else is happening in there. They're not as good as they used to be, and I've not found any way of reversing whatever happened in there. So they, from time to time, they do tend to stick, but I'm just going to have to work this out with the algorithm and then just give them more current and try to break them loose. Or maybe they will run in, but I don't think so. And yeah, so I'm going to put a second mirror on this Galvo. I'm going to make more position sensor with Hall effect sensors, and I'm going to glue them in right at the back of here, make sure that they're really close to the magnet, but not touching it. And once I have that, I think we can get to getting this done with software. And I'm going to write the software on a Teensy 3.2. These are a lot faster than the standard Arduino Nano, and they do have a much faster analog to digital converter, so they can easily go 2 channels with 25 to 40 kilohertz each, and that would be good enough for me. I just want to have these things move and I don't know, draw a line or something. I think I'd be happy with that. And the double H bridge chip that I have, this one is actually fine with working with 3.3 volts. That is enough to give it a TTL1, a TTL high signal, and the logic circuitry in in here is 5 volts, but it doesn't put 5 volt on the inputs. So this should work out fine. If it doesn't, then I'll probably need a level shifter, and we could probably make this work with just a very simple MOSFET level shifter. Not sure about. I think we can go without it, but if we need it, it's really simple to make. Yeah, so much for that. So the first thing that I want to do is I want to actually put the pins on here. They're just tacked on with one little solder ball, and I want to get these soldered, and then I think I'm going to try and use some breadboard and just get this thing set up on here and see how far we can get, if we can get any data from one of the position sensors, and if we get the data, if we can use it to move at least one of the galvos. So let's start. I don't want to put any burn marks on this cutting mat, so let's just put a piece of paper under the Teensy. If there's a little bit of noise in the background, it's either the smoke absorber from the soldering station, or it's the heating, because we had a slight temperature drop. It was really nice, above 20 degrees Celsius, and it just dropped to somewhere around 11 or 12. You might also be hearing the dishwasher upstairs, but there's no way that I can influence that. Okay, here we go. One soldered Teensy. Actually, break these off. And nope, we're going to go on that edge. This is a really, really old breadboard, and the old ones, the contacts are a lot smaller than we have on the new ones, because everybody used to stick resistors and stuff in there, and their leads are just way smaller. This thing is not getting in there. I might need to get something else. Is this thing working at all? This thing's probably seen better days. Whoa. I'll be back in a second. So, something of a fight later. I have the Teensy on the breadboard, and I've got my double H bridge and power supply on here. I have a power in that I can feed from a battery if I want to. And next thing that I would like to do is I'd like to figure out which ports on the Teensy I'm going to be using. And here we have the port sheet, and I think I want to leave everything open so I can have an SD card on here, which would be the SPI port, and I would have to use all the primaries on there. That means that we can basically use everything except for data 10, 11, 12 and 13. 13 is also the onboard LED. I think I want to use that. So we would have to reroute the serial clock for that to 14. And the analog input ports on the 3.2 are D15 is A1 and D16 is A2, which is probably okay to use because they don't actually also use something that we need. We're not going to use I2C, I think, and we're not going to use the touch inputs. These sheets they're pure gold. I really love them. They're so good. They come with every Teensy if it's an original, and these things are just great. So we're going to use A1 and A2 for the Hall effect sensors, and we're probably going to use, I don't know, D0 and 1 for the first Galvo and D2 and 3 for the second. Maybe if it's timing sensitive, we have to figure out if they're all on the same hardware data port, but for now we'll just do it the simple way. So I do have the two sensors that I pulled off the other experiment. I think these two here are the data ports, and this here is plus and minus, I would think. Unfortunately, I didn't mark them up, so we're going to figure that one out later. And we need to have them connected to 5 volts anyway. So we are going to use them on A1 and A2. And this board has actually been fighting me really, really bad, so I made this pin poker. I can just line this up and force the pins in. I think this thing has been lying around in the sun for too long. There we go. And this is, of course, completely wrong. because I would have the whole thing backwards. So good thing we checked. We do it right because we do it twice. Really love that saying. Okay, so we have the two Hall effect sensors hooked up, and we'll do the same for the A1 and A2 and B1 and B2 inputs for the H-bridge. So we need some copper wires for that. Hope that I have some. And I'd like some all copper if possible. This looks bad. Quite fascinating how all of these wires that you use for every project just seem to disappear. And well, they're about the right length. Of course, they're all the same color. So we have D0, D1, and we need one more here and another one here. That's going to turn out too short. And here we go. Put a little bit of solder on those so we can solder those. Fume extractor on. One. first one on, second one also about to go on. There's the third one. And finally the last one. And if you think that I left too much cable on here, I did that on purpose because I couldn't break them back off again. No, because I may have to put a scope to that to see if this is working as expected. And it's never wrong to have some bit of bare copper where you can attach a scope. So we do have plus 5 volt. We're going to grab those from here also. No, we're not. I think we're going to do that different. We just want to grab ground for now. And of course we did it all wrong because pin 1 is ground, pin 0 is ground, pin 1 is data 0, so these are all exactly one position wrong, and I bet half of them is going to fall off. Yeah. Right. Okay. Let's do this again. Man, this solder that's on here really sucks. This is really bad solder. That looks a lot better. Right, we want to do the same with the ground line from the controller, and we will be feeding the Teensy through USB. And this is connected to ground, so is this. We have 2 inputs on the Teensy. Now we need to figure out what the connections here are. So this is 1, 2, 3 on the Hall effect sensor, and one is plus, 2 is minus, 3 is data. One is plus, so this here is the positive. So we need another wire to connect up the negative. And we are going to use the voltage in on the Teensy, and I got that one right, to power the Hall effect sensors. And that is not a good idea, because we actually need them on 3.3 volt. But I'm not sure if the Hall effect sensors will take 3 volt. But 3 volt is on this pin here. Gonna have to find out if this works. But yeah, it looks like we've got the whole setup right now. The Hall effect sensors have power. Their output is routed to analog in 1 and 2. No, it's 0 and 1. Oh, what the hell, I'm just gonna leave it like that. And we have the data outputs 0 to 3 going to the bridge chip, so we can power 2 Galvos with 1 H bridge each. Is this gonna work? Yeah, let's try to program something for that. Okay, slight issue. The supply voltage and output voltage of the Hall effect sensor is, in fact, the input voltage is 5 volt and the output voltage is up to 5 volts too. So we need to have a voltage divider at the input, or we're going to fry the poor little Teensy. And we don't want to do that, of course. So I'm going to go and grab some 10K and 20K resistors so we can have a 3-to-1, 3-to-2 voltage divider. 10K and 20K. That's 20K. And here we go. Here we have some open 10K. So we are going to be connecting the 10K resistors to ground, and we're going to connect the signal via a 20K and that should help us divide down the input voltage. And this breadboard is really dragging on my nerves. So to 10K and to 20K and one of the two just went flying. So we need more copper wire. And of course, the only wire that I can find right now is white. Honestly, I have tons of this telephone wire, but I have no idea where it is right now. But it's not that. The circuit is so complicated that we couldn't just figure it out by just looking at it. That's one of them. And there goes the second one. I haven't fried a Teensy in, I don't know, over a year. But I'm not sure I'm gonna keep up this record the way this is going. Okay. Input, voltage divider, 2 to 1, so we're turning 5 volts into 3.3 volts, and we're supplying the output of that to the Teensy's input, and we're pretty sure that we're doing it towards ground. Yeah, doesn't look bad. So now we start figuring out what the software can do. So the software is actually super simple. It's not much more than a simple read on the two inputs and just printing them out for now. And if we have a look at the serial logger, we can see that we're getting some data. There's quite a lot of jitter on that but we'll deal with that later. I suppose that is just the sensors, and maybe it is also has something to do with the way that the Teensy is powered right now. Maybe we can improve on that. Yeah, but since we do have the possibility to use the sensors in here and to show that the serial data logger was working, I was basically just putting the sensor in the back of the Galvo and moving the mirror around, and that was enough to show us that we were getting some data that we could maybe measure against. I don't know if the resolution is good enough, but since this is more or less just a proof of concept, well, who cares? Now, we can also see the data on a scope. If I bring in my little scopey thing, and I have this set up, and if I bring this close to a magnet, we can actually see the data on this changing. That's the wrong sensor. So here we can actually move the data around, and we can see that we're getting different voltages, and this is all the way we expect it to be. And we can also see that there's a lot of noise in there, so I suspect this has to do something with this has something to do with the Arduino itself, and we'll figure that out after that. But we are getting pretty good data, and the attenuation works. Maybe you can see it. I did switch the resistors around because I had them wrong, but it looks like for what we're getting right now, the data is great. Now, the next steps are to actually wire up the H-bridge and maybe try and set a value that we try to position against. I think I will be picking the mid position, and then maybe we can move the mirror, and it should return to the middle, and we can then have the data on the data logger that shows us how it's reacting to that before we start getting into anything like PID calculation or anything of that sort. So first order of business will be to wire up the sensors, and I kind of decided how I'll just be sticking the sensors into the Galvos, and I'll be attaching them with just with hot glue, because I don't know if I'm gonna have to rework it. Should be the simplest thing. So let's get the hot glue gun fired up. And while we're waiting for that to heat up, we can prepare the wires for the H-bridge. I think I have a few wires here. Here we do. Let's just tin them up. Okay. And we're just going to put these in here. And we will be using the output with the one as the one that has the color, and the other one will be on the white one. Screwdriver. Screwdriver. Here we have our screwdriver. So this output is B1 and the other one is B2. And we'll be doing the same for A1 and A2. And that did not work. Why? Oh, because these are all bent out of shape. Oh, komm schon. Nope. So this board has been used before, and these screws are pretty worn in. Okay, now this here's input 1 and this here is output 1. So let's join them up on one of the galvos. I don't like the way these sensors are dangling back there, but can't help it right now. So next thing would be to try and go through the measurements again with the serial monitor and the serial plotter. So we have both of them connected. And we do get input from one. This is our first channel. And yeah, we have some useful information here. And we got the second one, which is also giving us good information, and the range appears to be the same for both sensors. Neat. Good. So, what do we do now? We need to make it move somehow. So, moving it is relatively simple. We just have to put one polarity on one side of the H bridge and the other polarity on the other side of the H bridge, which means writing 1 to one output and 0 to the other. That should get some current flowing, and we should maybe do it very gently just for a short amount of time and see what happens then, maybe. Yeah, let's do that. So the reason why it didn't work was simple and stupid, and I'm not sure if this was the reason that it didn't work before when I tried it this time. So I mounted the sensor 90 degrees wrong. When you were seeing me mount it in this video, the cables were pointing downward. This did work with measuring the position, but when I'm actually trying to modify the position, I want to be able to measure the position when it is not in line with the field that the coils can put on it. And that field is either this way or that way. So the sensor must be positioned this way, so it will actually measure correctly the position of the magnet that can rotate inside of that axis. And it did take me a while to figure that out, and when I'd figured it out, I was like, oh no! And I'm trying to look for old documentation and photos that I did of this project if I had these sensors in there, always in the wrong orientation, because I sure know that I had it wrong in these here. So yeah, that is sometimes how it goes. And I am now just going to try and turn this on, and we should be seeing this mirror here move back to front. And let's just do it. Power for the Teensy and power for the driver. And as you can see, it is working pretty nicely. It's not perfect because I have way too much of a dead zone defined, and I am basically limited to a very low frequency, somewhere around the 15 to 17 kilohertz, but it's working nicely. I would be able to go a lot faster with the Teensy, but I would have to use an entirely different way of writing the software, because right now I've got an interrupt routine, and the interrupt routine is reading the analog input, and that is slow. I could write the code so I have the analog digital converter running in a loop, and every time it completes a conversion, it would call the software to do the movement of the on the driver. But the downside of that is that I do have two different inputs, and although there are two converters in there, it is kind of hard to get them set up that way, and that would make the code really, really complex. And this is just a proof of concept, so I didn't want to go all the way with writing the software. I'm still pretty amazed at how well this is working, because it's actually driving both steppers right now. One is being told to stay in the same position, and the other one is being told to move back to front, back to front, back to front. And I really like it. This is basically where I wanted to get with this. Now, the next thing that I would like to try out is to first of all go a lot faster, and then maybe to have to put some kind of pattern on this and see how well this positions. But before we can go into the more complex positioning, I think I'm going to have to think of some sort of PID algorithm for the stepper driver. Although right now this is just a proportional drive. It measures the difference between the position it has and the position where it wants to be, divides that by 4, and that is the input value to the driver. And the driver then sets up a PWM, which is always driven by the frequency of the interrupt loop, and this is divided into 200 parts, and it can have 200 different iterations or 200 different powers that it can put to each stepper, and it will just calculate them, and depending on the value of the power that it wants to put on it, it will have a longer duty cycle for the PWM. That is the short gist of it. And we can actually see this. I'm going to bring in the El Cheapo, the little oscilloscope, and I'm just going to hold on to this thing and keep it in one position and tell it to try and find an auto setting. And we can actually see the PWM moving right now, and we can see it jitter from one position to the next. And I can just hold it at 1 and it should pretty much show the difference. It's not doing it really well. Yeah, because I'm I'm turning the wrong motor. So if I give it a large error, you can see that the duty cycle becomes bigger, and if I let go of it, it becomes really fast and really small. And what you can also see is that because the two magnets actually influence each other, I never really get to the correct position, which is kind of not really what I want, but I suppose that is just the implementation of it. And yeah, the frequency of this is, I don't know, around 16 to 17 kilohertz, and it's really annoying. Yeah, but as you can see, this is working pretty nicely. The more error I put in, the larger the duty cycle gets, and I can almost get it to become a full, this is the full duty cycle. So I do have a little bit of lead out, so I can basically prepare the sensor for the next measurement. So I make sure that I don't measure the magnetic field of the coil, but only of the magnets. So there's a window in there where there's just no coil current running, and in that window I do the measuring of the magnetic field. So I make sure that I'm only measuring the magnets, and yeah, that works. It's really nice, in fact. Okay, yeah, so I'll now try and make this here go a little bit faster. This should be pretty straightforward, because the only thing that we really need to do is we need to change the software to go faster. And we're just going to fudge that a bit. So we have a very simple deadline scheduling here, measuring the current time and telling the loop when the next 500 milliseconds have elapsed. And I'm just going to lower this down to 200 milliseconds, and I'm going to send this to the Teensy, and let's see what happens. Nothing happens. Oh yeah, so it's uploading, and now it's a lot faster. And the positioning is still okay. I don't know, I don't think this would be good enough for an SLA 3D printer, but the way it looks right now, it could possibly be made to use for one. We would have to go a lot faster to do a laser show or something in the like, but it's close enough, I would say. It really is. So yeah, I think that sort of proves it that this works. I didn't want to make this video so long, but it actually, except for when I had to take some time off for food or sleep or something, I basically had the camera running most of the time, except for when I was doing the coding, because that would probably have been really boring. Yeah, this is how long it takes to do this. Hope you enjoyed it, and thank you very much for watching.